Let us do the signature assignment first. But I guess before we get started, let me remind you that we have a week 10 meeting that we have to do. It's online. It's on Thursday of week 10. I don't remember what time, but it's scheduled for 2 hours. We probably won't spend that whole time. We'll just do a couple of activities. And I'll send out a Zoom link. I'll make an announcement on Canvas with the Zoom link and everything. So I do not remember what time it is. I'll also post that for us. Okay. Ready for the signature assignment? Mm-hmm. Excellent. So there's the PDF. You've all got a paper copy of that now. And there's also the list of 500 heights and shoe sizes. Go ahead and open that up on your computer. It's a list of 500 heights and shoe sizes.
Where is it under?
Look under the Week 9 tab. Should be right there.
Under the announcements?
Signature assignment.
No, under the Week 9 tab. We do not have a Week 9 tab?
Yeah, when I click on signature assignments, it pulls up the PDF, but no other.
Okay, ready? Found it.
You found it?
Yeah. Home, and then the signature assignment. And then there's a video, and then right above the video, it says heights and shoe size of 500 random people. Click on that, and then it'll open a PDF. Is that too fast?
Home and then signature assignment from the home page.
Yeah, and then, because it says like week 1 and 2.
Oh, there's a signature. Instead of it being...
Oh, I got it.
And then right there, heights and shoe size, that's the link to the PDF.
Got it. Ooh. Glad we didn't have to print that. Heights into a page.
See?
All right, so this is, as advertised, a list of 500 heights and shoe size. It has the corresponding number, just like their name, but it's numbered. Why do we want this? Because we want to do a systematic sample. The assignment wants the sample to be size 9. So we're going to have N be 9. You should decide on what your system will be to capture that sample. So for example, I could say I'm going to start at number 35, and then my step size would be 6. Okay, so then the first one in my sample has number 35, right? And the next one is 35 plus 6. And then the next one is 35 plus 2 times 6. And then 35 plus 3 times 6. And if I'm going to do it like that, then this was really 1 times 6, and this one was 0 times 6. Well, then now I can easily know where I should stop, because it goes 0, 1, 2, 3, 4, 5, 6, 7, 8. And by the time I get to 8, well, that's the 9th one. So I'll just keep on going until I get to 35 plus 8 times 6. I can explicitly find what all those numbers are pretty readily, and each of those heights and shoe sizes are numbered, right? So I would do number 35 and then number 41, and then 35 plus 12 is 47. And I just add 6 again to 47, get 53, and so on. And then my last one here would be 35 plus 6 times 8 is 48. So 48 and 35 is 50 and 33, so it's 83. All right, and that's a systematic sample. And then you would describe that sample that you took, you would describe this methodology in question 1. It was a systematic sample from the list of 500, and this was my system for picking the numbers. You would state your system as follows. So for me, it was 35 plus n times 6. This tells me where I started and how far I stepped over. The n just varies from 0, 1, all the way up to 8.
So then you just randomly do 6?
I randomly pick 6. I randomly pick 35. You can pick anything, as long as it terminates before 500. So then I guess I would write something like I used a systematic sample of and then that completely describes what I did. And I guess I should see what else it's asking for on the assignment. They're wanting to know what is the population, so I should state that this came from the population of the list of 500 people.
So when you start at 35, are you starting at the person's number 35?
Yeah.
Okay.
Yeah, so that numbering, I added that numbering just for this semester because it used to not be there and we have to count by hand.
Oh, jeez.
So now at least you can figure out exactly which number you're needing and just go straight to it. Like, because what if you pick something that's not 6? It wouldn't be as convenient to go 1, 2, 3, 4, 5, 6 and get to the next one. You could pick 30 if you wanted.
But you're using the number 35, not the person's height or shoe size.
Someone's not going to be height 35 on that list, right? Or have a shoe size 35.
Okay.
So yeah, these numbers that we're talking about here are the first column. It's like their name. You know, the systematic sample is where, you know, it's like picture a factory when there's stuff coming on the conveyor belt, you know. You have the first one and the second one and the third one. And how do we make our sample from in that type of situation? Well, it'd be something like this. I'm going to grab the 35th one and then check the next 6th one after that and so on until I have whatever sample size I want. And that's the place where a systematic sample is usually used. For whatever reason we're doing it, we have to do it here too. All right, the next thing that they ask is where and how are you going to collect your sample? Well, we already answered that because we said it's coming from the list of 500. We said how because we used the systematic sampling method like it says to do right here. The last 2 questions, don't worry about it. Does your sample accurately represent your population? Why or why not? Those are actually not answerable. They shouldn't even be there. Okay, so then you'll get your numbers, you'll get your heights and corresponding shoe sizes, and then just write them in this table. You understand what I'm saying? So like for me, height, the 35th person is here. They had height 64 and shoe size 9, so I'd put 64 to 9 right there.
Okay. And then the second person would be 35 plus
6.
1 times 6.
Mhm.
Okay.
So for me, that'd be person 41. And 41 was a 70 and 11. So. And you just keep going till you get them all filled out. Here, I guess I should get some because I'm going to need some data.
Really quick question.
Yeah.
For your person number 2, you got that from what you were doing at first. So I used like the 35 plus the whatever.
Yeah.
Okay.
I mean, don't use 35 and 6. You have to pick your own number.
Yeah, I did.
Okay. But yeah, so 35 and 6, that's 41. So person number 41 is right here. That's 70 and 11.
Okay. I keep trying to put, never mind. I keep overcomplicating.
And then I just add 6 to that last number to get to the next one each time. So number 47, that's 68 and 9. And then 53 is 65 and 6. 53 plus 6 is 59, so I'd be at 73 and 12.5. And then plus 6 is 65, so it's 67 and 9. Number 71 is 64 and 11.5. And then 77. 49 and 3.5. And then finally 83, 70, and 11. All right, so now I've got all 9 of my data points. You have this first row is 9 numbers, the second row is 9 numbers, but you can also pair them up, by person. So then this pair of numbers becomes 1 data point. And this pair of numbers is 1 data point. It's an ordered pair. And then so by the time we get to the end of the assignment, we'll plot it with our best fit line. But first, we would have to do a bunch of other stuff. So the first question they come to is we need to pick our confidence level. And you are encouraged to pick one of the 3 normal ones, 90% confidence, 95% confidence, or 99%. Does not matter which one it is, but you would write down what alpha would be. You wouldn't write down 90, 95, or 99, right? Because these 3 numbers are what 1 minus alpha is. 1 minus alpha, that's our confidence level. It was this picture. 1 minus alpha is here in the middle. And you have alpha over 2 in that tail. You have alpha over 2 in this tail. If you add the 2 alpha over 2's together, they're just alpha. 1 minus alpha plus alpha is 1. That's all the area under the curve.
So if I did the 95,
Yeah.
the copies over 2.5.
That's what alpha over 2 is. You're just supposed to say what alpha is.
So it's this
5%.
one. Okay.
Well, so 5%, right?
Right.
0.05. Yeah.
Right.
Okay, yeah, 0.05. So I'll do that one too, 0.05. And then consequently, this alpha will be the maximum amount of risk that we can take in rejecting the initial hypothesis. No more than 5% risk. All right, so there's my numbers, and let me snap a picture of this real quick, because now I need to go to StatCrunch and type these numbers in. So I just go to any assignment on in my lab. Oh, I guess I didn't need a picture, they're still written. And click Get More Help and StatCrunch. StatCrunch opens, it's just blank. I did all that just to be here, right? And my first column will be heights, and my second column will be shoe size. And I've got the numbers right here, so 64, 70, 68, 65, 73. I get all my heights typed in, and then now I'll put in the shoe sizes. So 9, 11, and 9, and 6, 12.5, 9, 11.5, 3.5, 11. All right, part 2A. Find the sample mean and the sample standard deviation of the height. Denote them as x bar and s sub x. So x bar would be my sample mean, and we have to put this little subscript on the standard deviation because we need to distinguish between this standard deviation and the standard deviation of the shoe size. And these are our x coordinates. They're going to be on the horizontal axis. This down here will be s sub y. Okay, well, I can do this pretty easily. In fact, I can do it just in one take, right? So summary stats columns, and I just pick both of them. I don't even have to do them one at a time. And click compute, and then there it is. So I'm getting an x bar of 65.556. 3 decimal places is plenty. And my standard deviation is this 6.912. Make sure you're using the standard deviation and not the standard error. All right, and then I need y sub r and s sub y. Okay. Y sub bar, or Y bar is 9.167. And S sub Y, 2.861. And I don't even have to close this window. I could. If you close it and need it again, you don't have to go do everything again. Here, I can close it, and then it is right up here, right? Comes right back in. All right. Super. So, oops. So now I've got A and B done. Construct and interpret a confidence interval to estimate the height, the mean height. So here's what I want you to do here. We are going to say that the answer here for the confidence interval of the height is x bar plus or minus t sub alpha over 2 times s over root n. And that in turn, this is equal to 65.556 plus or minus, and I'm just going to leave a space right here. I'll get that number here in a minute. And S, so this would actually be S sub x right there. And then this would be 6.912 over the square root of 9, which of course is 3. So now I want to get that t sub alpha over 2 number. We should go back to StatCrunch and open up the t calculator. So stat calculators t. My degrees of freedom is n minus 1, so that's 9 minus 1, we have 8. And I put it on between, and since my confidence level was 95%, then this would be 0.95. So my t sub alpha over 2 is this number. $2.306. Okay. I won't have to look up that number at all again because it's the same throughout the whole. You only need it in one more place, and that's in part D. It'll be exactly the same. Now, you're more than welcome to use your calculator here to compute that number. However, now that you all have paid your dues by doing it by hand, I will show you how StatCrunch just does it immediately. we have our data stored right there, yeah. So I can just go to t-stats. It's t-stats because we would have to use the t calculator to get that number. And then one sample with data. I have the data. I'm doing it for heights. I'm doing a confidence interval. So just scroll down to the confidence interval part. Make sure that the level matches what I wanted. And compute. You get your bottom number and your top number. So I'd be saying that it's equal to, and I'd write it like this, 60.242, comma, 70.869. And that's my interval. And it exactly matches these numbers before it. Right? We could we could use our calculator and compute this, and we would not be surprised when we got these numbers. Okay. Construct an we didn't interpret. The interpretation would be what do you think?
You use 95%, so you're 95% confident that the average shoe size for those 500 people is 60.24.
Contained inside this interval. Perfect.
That one's a height, so it's 95% straight up.
Oh yeah, good call on the height.
Yeah.
Would have been huge shoes.
And then we're supposed to do the same thing in part D, but now it's about the shoe size. So it's y bar plus or minus t sub alpha over 2 times s sub y over root n. And so I'd have 9.167 plus or minus. It's the very same t sub alpha over 2, 2.306, and then times my s sub y, which was 2.861, over the square root of 9, which is just 3. You can write 3 or you can write square root of 9, whatever, it's the same. And then we can write down our interval. once we use StatCrunch to get the numbers. So here I still have my T-stats open. I can just go back to options, edit, and change it to shoe size.
When we did it the first time, you can highlight both.
You can, yes.
Okay.
Really quickly.
Yep.
You went to stat and then.
T-stats
T-stats and then one sample with summary.
with data.
All with data.
Yeah. You could do it with summary. We have the numbers, right? It's the mean and the standard deviation.
Oh,
But this is even faster
right.
because the data's right there. All right, so my interval would be 6.967 to 11.366. Now that's the numbers I get, but they don't make shoe sizes like that. Right? So we need to round. Let me ask you, if your foot had this requirement,
Get a size 7,
you need a size 7. If your foot had this requirement,
11 and a half.
11 and a half. So then my actual interval is 7 to 11.5. You always have to round up or else your toes hit the front. All right. Let me write a different interpretation this time, because the one we did have is certainly fine. We're 95% confident the mean height is in the interval. But it's equivalent to say that that if we had done 100 samples, we just did one sample from that population of 500. If we did 100 samples, then 95 of them, or I'm sorry, let me say it again. Yeah, if we did 100 samples and got 100 different confidence intervals, 95 of those confidence intervals would actually contain the mean. So for 100 samples with 100 different intervals, right? Because there's no reason they should be the same every time, because you've got different people in your sample every time, right? You would get a different confidence interval every time. They'd be similar, but still different. So for 100 samples with 100 different intervals, 95 of them would actually contain the population mean. Up next is part 3. We have a hypothesis test. Test a claim that the mean height of your population is different from 64 inches. So, my initial hypothesis is that the mean is 64, and the alternate is that the mean is different from 64. We're going to use that alpha from earlier. Alpha was 0.05 for me. Find the test statistic and p-value, so we should stipulate what that formula is. It's the observed height, x bar, minus the mean over the quantity s sub x over root n. And I want to just write down what those numbers were. So x bar, I can go back and get. Mu, I know, is 64. And s sub x, I'll have to get what that is, but the square root of n is 3. Okay, so x bar was 65.556. And S sub x was 6.912. Again, you are perfectly welcome to calculate that. However, I'm going to go over here to StatCrunch. And go right back to where I was a minute ago. T-stats, one sample with data. I'm going to pick the heights. And now I'm going to do a hypothesis test instead of a confidence interval. And mu is 64, or it's different from 64, and that's it. And I click compute. So it gives me the test statistic and the p-value. That is exactly what I would be getting if I had performed this computation. I would have performed this computation, I would have gotten my test statistic. I would then punch in that test statistic into my T calculator and I'd get that p-value. Well, I'd get half of this number right here, right? Because this is a two-tailed test, I'd had to double that area and I'd get this. So my test statistic is 0.675. 0.675 is really close to 0, so our p-value naturally is going to have a lot of area. You only get a small p-value if your test statistic is far from 0. So having this big of a p-value, what's going to happen? What is the outcome of our test? What is the p-value in terms of a probability? This is the probability of something. What is that thing?
Of, it being located in
This is the area of the two tables
Yeah.
formed by this test statistic. The positive version of this and then the negative version of this. And this number is the sum of those two tables. But what is it the probability of? What event? The test statistic, or excuse me, the p-value tells you.
probability that the height is greater or is not equal to 64.
Talk to me about the probability of being right or wrong when I do this thing. What thing?
Reject or not reject.
It's the probability of being wrong if I reject. I don't like to be wrong. And this says that there's a better than a 50% chance that I'll be wrong if I reject, so I shouldn't. I'll fail to reject.
So if it's under the 50%, you would reject instead of fail to reject?
No.
No.
Mm-mm.
P-value is less than the level of significance.
Significance level. The alpha is the limitation on the amount of risk that you should take.
Okay.
Yeah. So we could only reject if this had gotten underneath 5%. Because even if it was under 50%, that's still a massive amount of risk of being wrong. Like you want some assurance that your decision is right.
Never mind. I was
So
looking
my
at it wrong. I thought it
p-value
said 50% instead of 5%,
Oh.
but never mind.
So it's greater, the p-value is greater than the level of significance,
Mhm.
greater than the alpha,
And yes, it is, right?
which means you fail to reject.
Yeah.
Because there's not, because that's probability of you being wrong.
If you were to reject.
Okay.
Yeah.
So you fail to reject it. So-
Yeah, yeah. And that's gonna be part of what our informal conclusion is here in the next part. So informally, I would say that there's a 51.86% chance we're wrong if we reject. Formally, however, we would say fail to reject. There's insufficient evidence to support the claim of the alternate hypothesis. All right, question 4. find a correlation between height and shoe size. Part A is create a scatter plot of the data with the height on the x-axis, shoe size on the y-axis. Attach this to the end of your document. So what you'll do is, for now, we're going to take a screenshot of it. So we'll go to StatCrunch. Stat regression simple linear. The X was heights, the Y was shoe size, and that's it. Click compute. And you get a 2-page summary. And so then this is the image I want. And does everyone know how to do a screenshot? So you'll get that screenshot and save it somewhere where you can get back to it, right? Because it'll just be one of the things we upload when we submit. Super. And then back here on page 1 has all the rest of the stuff that I would need to discuss. Because now they ask me to find the linear correlation coefficient. And what does this tell you about your data? Okay. Well, my linear correlation coefficient is 0.8384. So this is a lowercase r. R is equal to 0.8384. It tells me that there is a strong positive correlation. If it was like 0.5 or something, it'd be a weak positive correlation. If it was 0.3, it'd be very weak. If this was 0.9, it'd be very strong. Okay. So there's some kind of correlation. And the true process we would use is the p-value process, right? So my p-value here is 0.0047. Okay, so that's a very low p-value, and it tells me that I absolutely would be using the linear model, not y-bar. However, the instructions on the assignment have you use the linear model regardless. Okay. So let's see what the next question is. Write the equation of the regression line and use it to predict shoe size of someone that is 68 inches tall. So y hat is equal to a minus 13.587 plus 0.347 times x. So there's my equation, and to use it, I would be saying minus 13.587 plus 0.347 times 68 is equal to, well, let's see. $10. Okay, I'm going to stop here and check for reasonableness. Does it seem reasonable that someone, let's see what this is, a 5'8", could wear a size 10 shoe? I guess so.
I'm 5'8", and I wear a size 10 shoe, but in women's.
How about that? Well, so we didn't. It was never said in the paper if it was men or women. We just completely ignored that. Yeah, I was looking at a submission the other day. Someone submitted early in the online class, and I was like, "You need to go back and look at this." It was like Shaquille O'Neal was a size 22. So, just for comparison. Yeah, so checking for reasonableness there is a smart use of our number sense. And look at that, we're at the end. So, write a paragraph or two about what you have learned from this process. Let me see, I've never actually written anything here. Let me think of what I would say. Did y'all see that announcement that I made where it says I Googled who was the first statistician? I didn't doctor that or anything. I had an expectation that her name would be on the list. Well, I did, so I did not know that it would be on the list when I did it. But I wondered if it would be, because she was.
Yeah, I'm also in microbiology right now, and they talked about the stats that she used.
Mm-hmm. Yeah, she pioneered certain techniques and methods. There's special charts named after her. Wars were won because of her statistical study. All right, so that is the end of the signature assignment. Now, when you get finished with it, you should photograph the pages with your phone, right? And then I would assume that you could then submit right from your mobile device. So it might be better though to like send them to your computer, because then when you do your submission, you'll have the photos of the paper, and you'll also have the screenshot of the chart. So in total, there would be three files attached.
Why 3 files?
Side 1, side 2, and then the screenshot.
I did DocuSign scan, so.
Yeah.
Okay. I don't want you to be like, June, you don't have that.
All right. Well, let's take a quick 10 minutes, and then we'll come back and do our business with the funding, which should be very easy now that we can use StatCrunch to do our confidence intervals and hypothesis tests.
Did you take microbiology in person?
Mm-hmm.
Did it online?
What numbers did you guys use?
I used 21 and 7.
That's 20 and 4.
Today's the day I get my badge, I decided. This is my only class on campus and I get just leave the building, forget about it. Come back the next week, oh, I gotta do that.
Yeah.
It's not that hard, you just have to take a picture.
But you gotta be careful. Because for my new work badge, I did not know I had to take a picture that day, and it is
You're like,
less than ideal. And you have to wear it, like,
every day.
as close to your face as possible, and it's like, cool, cool, cool.
Be ready.
Don't start anything yet. We'll make a change.
Last week I was in the middle of redoing one of the timed midterms
Uh-huh.
when the tornado alarm went off at my house. Like,
Yeah.
All right, we better hustle because this is timing.
I just wanted all the questions to go in order. All right. So then we should always be on the same type of question. You know what I'm saying? Okay.
Can we start it now?
Yeah. All right. Well, I have the number of murders. Cheery topic. Number of murders in different cities in a certain year. They want to know if it's discrete or continuous. What do you think?
Discrete,
Why?
because it's in a certain year and there can only be so many murders.
The number of murders is countable.
Yes.
Even if we murdered everyone and then they murdered themselves, it would be a finite number that you could label each one of them 1, 2, 3, 4, 5. So it can only take on these specific values.
Good question.
Yep.
Because this always, so like, you know how the wording on the, what it says is on the prompt. So you know how yours said a certain year?
Yeah.
If it just said a year,
Yeah.
you know what I'm saying?
It'd still be, so the rest of that doesn't even matter. They could have just said the number of murders
Okay,
because I could count them. It
right,
could be the number of copy machines in America.
right,
You can count them.
okay.
Determine which of the 4 levels of measurement is most appropriate. Volume of brains in cubic centimeters. If I could rewrite that question, it would say possible brain volumes.
I have one more question. I
Yeah.
feel like I'm overcomplicating it.
Oh, what's up?
So, for mine is just like weights and tons, right?
Okay.
And I understand this is discrete.
No.
No.
Weight, time.
I'm still not.
Because like how much does a car weigh? 1.6874 tons.
Right.
Your car weighs a different number of tons than mine.
Mm-hmm.
There's a difference between saying the weights in tons of all the cars that exist. That's countable. But the weight, the collection of all possible tonnages is uncountable. all I gotta do is go out to the millionth decimal place and change one number, right? I can sit there all day and make uncountable list of different possible tonnages.
Okay, I get what you're saying.
Yeah.
Because any value of an interval.
It could be any value in an interval.
Specific. Okay.
Between 1 ton and 2 tons, there's uncountable collection of different possibilities. It's the same thing here for for possible brain volumes.
Right.
It's uncountable, but here they're asking me for the 4 levels of measurement for a brain volume. Well, the smallest, I mean, if your brain shrank down to nothing, I mean, shrink it down to 1 cell and then take that cell away, the volume is 0. And if they weighed my brain and compared it to her, I guess measured the volume of mine and compared it to Einstein's or whatever, the difference would tell us something. It would literally be how much bigger his was than mine or whatever. So this is what? Ratio. It starts at 0. The differences are meaningful.
But they may not be correlated
They may not be.
to intelligence.
They may not be. Ravens have like are as intelligent as a small child, they say. A small child is a way bigger brain. Identify which of the types of sampling is used. Okay. Deborah's dividing up her day. She's partitioning her day. And then she measures her body temperature at 2 times per day. So it's a partition. It's stratified. For it to be cluster, she would have had to randomly select one of these partitions and check at every single point. You'd be there all day long, all morning, measuring your temperature.
Just keep the thermometer in
Yeah. The table below shows the frequency distribution of the weights in grams of some old quarters. I'm just going to look at the table. It goes, it peaks at 12 on the 5th row. So then I should be picking the chart that has its 5th column as the tallest one, such that that 5th column is also equal to 12. So it would have to be this one. It can't be that one because that's taller than 12. It can't be the 3rd one because the 5th column is shorter than the 4th one. Does it depict a normal distribution? Yes, because it increases to a maximum and then decreases and is roughly symmetric. Make sure you're careful to read that it increases and then decreases. One of those says decrease then increase. Okay, we have F-scale intensities of recent tornadoes. Remember the movie Twister?
Yeah.
That was a long time ago.
I think it just celebrated like the 25th anniversary or something.
Only 25 years?
Maybe 30.
I can imagine.
I'm missing
I watched it on a laser disc.
that. Ooh.
That was before DVDs even came out. All right, so what are we doing? Frequency polygon. Well, the frequency polygon is just a histogram, right? The dots are in the top, the middle of the bars. So I should be looking for the one that goes 22, 19, 2, 1, 1. Sure does look like it's A, this first one. Sure enough. And your frequency polygon must connect back down to the horizontal axis. So you have here 22, and then 19, and then it way drops down to 1, 1. Is it skewed? Well, which side is the tail on?
Right.
All right, so it's skewed to the right. And what does skewness really mean in terms of the mean and the median? Because looking at tails is not really rigorous math. It just coincides that it just happens to be the case that that works. When you're looking at a distribution shape like that, your median is at the tall part, right? Look at how many F-scale tornadoes were in that category. There was 22 of them that were F0. So the majority of the tornadoes are down here around at 0. You see how I'm trying to get this figured out here. Right, we have the majority of them down here. So if I made one long list that meant 0, 0, 0, 0, 0, 0, had 22 zeros, and then it had 19 ones, and then 2, 2, 3, 3, 4. That would be our list of data, and the median is the number in the middle. So it makes sense that the median would be right underneath the tall part. However, if we figured out what the mean was, it would be to the right of the median. And that's what it means to be skew right. Yeah. Because our data would be 0, 0, 0, a bunch of zeros. There would have been 22 of them, and then 1, 1, a bunch of ones. There would have been 19 of those, and then 2, 2, 3, 3, 4. I could add all that up and then divide by how many, and that's my mean, and it's going to be bigger than 0, right? The median is 0, and it's going to be, well, the median is close to 0, and it's going to be bigger than that median, for sure, because of the 4s and the 3s. In reality here, the median is probably 1, because there's 22 here, and then 24. So the mean is to the right of the median, or the tail's on the right, it's all the same. 11 players from the championship sports team. And it's their ages. And they're a championship sports team. Not a they weren't randomly selected from the league. So they want the mean, median, mode, and mid-range. Click the icon to view jersey numbers, data, and statistics. Let's see what it says. Useless though, right? Okay. So I can open this in StatCrunch. Stat, summary stats, columns, VAR1, and compute. All right, so the mean age is 28.4. And the median age is 27. I didn't pick mode when I did it. I'll just inspect it manually. I see that the mode is 25 and 31. So even if I had done it in StatCrunch, it just would have said multimodal, and
That's what mine said.
and I'd have had to do it by hand anyway. So, 25 and 31. Find the mid-range. StatCrunch cannot do mid-range for you. You have to do it by hand. It's quite literally the halfway point between the maximum and the minimum. So the minimum is 20, the maximum is 41. Whatever number is right there in the middle, it's our mid-range. You can calculate it by taking the average of those two numbers. So 20 plus 41 over 2. So it's 61 over 2, that's 30.5. How are the resulting statistics fundamentally different from those calculated from the jersey numbers of the same 11 players? Well, the jersey numbers are data at the what? Nominal level of measurement, but the ages are data at the ratio level of measurement. Because your age starts at 0, differences are meaningful. So, only the age statistics are meaningful. All right. 11 jersey numbers of a randomly selected football team. Then with the range, variance, and standard deviation. So summary stats columns, VAR1, compute. My range is 82. My standard deviation 31.6. And there is no point at all in actually discussing the variance because it's a number that we don't have any intuition with. It's the standard deviation squared, right? We're not talking about, how big my apartment is in square feet. That would be like a useful place. If I told you what the lengths of all the walls were, it wouldn't be useful to you, right? You would want to know what the square footage was. And in the same regard, the variance is useless to us here. What?
Hey, accidentally clicked submit S.
Oh, but it gave you
But it gave me an out. It gave me an out. Oh, guys. Whew.
The variance is almost 1,000, 998.8. What do the results tell us? Nothing. All right, we all at the same spot? Percentiles. Use the accompanying radiation levels for these 50 different cell phones. Find a number, not necessarily one of these data points, but a radiation level that is at the 90th percentile. Okay, well, which position should I look at out of these 50? Which position should I look at out of these 50 such that it's 90%? Well, that's the 45th one. Yeah. So I'll go to the 45th number. It's going to be in the last row, right? That's number 41, 42. Number 45 is right here. But I can't use that one. I can't use this one because it does not have 90% of the data underneath it. I need to use this one because that's the one that has
with that you did 40, but well not 40, it would be 45.
yeah. So so what our calculation computes here is that I should find a number, a radiation level, for which 45 of these are less than it, strictly less. And so 1.39 would do it. 1.4 would do it. But and it's configured to take several different answers, but we can just go to the next one, number 46, because number 46 has 45 numbers under it.
So if mine is 10, I would just go 10 down one.
Up one. Yeah. So then you had what, 20%? They want P20?
P10.
They want P10.
Mm-hmm.
Okay. But I'm supposed to have P90. I didn't go to the 90th one.
Mm-hmm.
Right? This is trying to say, what is 90% of 50? That's what X is. 90% of 50 is 45. So you want 10% of 50. That's 0.1 times 50. It's 5. So you want the data, you want the number that has 5 data points under it. That's the 6th one.
Okay, so mine was P80, so it's 80% of 50.
80% of 50. Yeah.
And I go to that number, go to 40.
Well, you want 40 numbers under it, right? So whatever number 41 is. Now that's assuming that number 41 and 40 are different. You know what I mean? Because the definition says it has to be strictly less. So if it turned out that number 46 here was also 1.38, then I could not type 1.38. All right. We good? Time to engineer some babies with our technique here. Only 5 males were born out of a total of 297 babies. Am I right? Let us make a quick probability table. So Now that adds up to 1. It has to, right? Because I just divided by 297. I can see what the, that fraction is the probability. They're asking for it to 3 decimal places, so 292 divided by 297, because they're wanting female. And I get 0.9832. Or just 0.983. That's way effective.
So mine was closer to half.
Not effective.
Really effective, okay.
We can do that without their technique, right?
Right.
Okay.
Okay, wants a decimal, not a percentage.
Right. 3 decimal places. College students are randomly selected and arranged in groups of 3. And we're going to ask these groups of go around to each group and ask them if they take an online course, take 1 or more online courses. So then this constitutes all the possible answers. None of them could take it online, or 1 or 2, or all 3 of them could take an online course. Is it a probability distribution? Well, if it adds up to 1, then yeah. So let's see, 3, 6, 9, 7, 8. Just add it up real quick just to make sure. Yes, so mine is a probability distribution because all the probabilities added up to 1. I want now the, do we remember another name for this? That's what it's called right here.
Mu.
That's the name of the symbol.
Someone else.
Expected value.
Okay.
It's the expected value. This is a probability table. And we have some outcomes here. When we studied expected value, we had dollar amounts here. But all you need is a number. So that mu that we're going to get is just this times this, plus this times this, plus this times this, all the way down the table. However, we're going to go to the custom calculator. So I'll open in StatCrunch. Stat calculators, customs all the way at the bottom. Values are in X, the weights are the probabilities. Expected value is 1.579, and then there's my standard deviation. They wanted just 1 decimal place, so I'll put 1.6 and 0.9. So one interpretation would be that 68% of the time, when I go up to one of these groups of 3 students and ask them how many are taking an online class, I'm going to get an answer in this interval of 1.6 plus or minus 0.9. So it's basically 68% of the time you'll get 1 or 2. And where does the 68% come from? Well, I'm adding and subtracting how many standard deviations here? 1. I'm adding and subtracting 1 standard deviation. You can feel free to go to that normal curve and say -1 to 1 And it will tell you that the area here is 68%. That's empirical. It was 68, 95, 99.7. 99.7% of the area, so almost nothing happened more than 3 standard deviations away from the mean. IQ scores are normally distributed. And so we'll be calculating the probability that a randomly selected adult has an IQ between 80 and 115. So stat calculators normal. My mean was 100 with a standard deviation of 15. And I want to look between 80 and 115. So 75%, 0.7501. Still with the IQ scores, this would be answering the question, 97% of adults have an IQ score higher than what? So I'll put it back on standard and greater and say 0.97. So 97% of adults have an IQ higher than 71.8. All right, we all good? Yeah.
I was stuck on the other one, but I got it. Can you go over that one right there, the one that you're on, one more time? How did you get to use the same normal calculator?
Yeah, it's the normal calculator, but I have to set it to greater than so I get an area to the right of something,
Okay.
and then just tell it what that area should be.
My computer's just loading.
Still loaded? Is it froze?
That looks like.
Here we have Emily's experiment with psychics. What do you mean?
So the one that I just asked you about, so when I put it in, like the graph isn't matching up.
Okay.
The graph that it shows me.
Mm-hmm. Where are you putting the 0.97? Did you put it in the area? Or did you put it for the z-score?
I put it in, so I have to try this one. I have to do it in 80. Never mind, I got it.
You got it?
Yeah, I don't know what I did wrong. Yes, I do. I know what I did wrong. I just put it in wrong. I put 0.8 to, no, I put 0.08.
Oh, 8%?
Yeah, that's all it was.
All right.
So,
Excellent. So, what proportion of correct responses would be expected if the psychics made a random guess? Well, she's just flipping a coin. So it's 1/2. If she was rolling a die, it'd be 1/6. If it was 6-sided, so. Random guess between two options, 50%.
She really is like it.
What is the best point estimate of the therapist's success rate? Well, that's the quotient of the number of times they were right over the number of times they tried. That's p hat. That's 148 over 307. Say what? So in this 307 trial experiment, they were only right 48% of the time. 0.482. But I cannot use that information to justify that they are always doing a little bit worse than a random guess. It could have just been that this is the way the cards landed on this experiment, and that if I repeated it later on, they might do way better, or somewhat better. We want a 95% confidence interval. All right, so I'll open StatCrunch. Proportion stats, because we have a p hat, right? Proportion stats, one sample, and here it's with summary. We don't have the data. They were right 148 times out of a total of 307. And I'm doing a confidence interval. And it is a 95% confidence interval for me. So I compute and I get my lower limit and upper limit.
What did you get your, never mind.
Being sure to round as appropriate. What does this suggest about the degree of their clairvoyance? Well, 50% is contained in this interval, so it's entirely plausible that they have a technique no different from a random guess. However, the entire interval is not below 50%. If it were, I could conclude that they do worse than a random guess. Likewise, if the entire interval were above 50%, then I could say that they do something, they are clairvoyant, they're doing something better than a random guess. So just having one side of the interval be above or below 50% only tells us that 50% is inside here, that it could plausibly be 50%. But you cannot conclude that sometimes they'll do better, right? Because it could be the case that P is actually 0.43, and we just don't know it. 0.43 is in here. If it was 0.43, then that's always worse than 50%. Right? So I don't actually know that they can sometimes do better than a random guess. All I know is that because the whole thing wasn't above 0.5, we have absolutely no evidence that they can do anything. Egyptian skulls. I've got the raw data. So I can just click it, open in StatCrunch. And say with data this time instead of with summary. So T-stats, one sample with data. Tell it where is my data. And we're doing a confidence interval, and they want it 95%, so there we go. $128.79 and 138.68. Still good? Alexis, did your computer
Yeah,
cooperate?
I just need to go back to 13 whenever I need something.
Okay. Yellow peas.
Woohoo.
Let's see here. So we've got an experiment. 1% significance level. Oh, we're doing a hypothesis test. So alpha is 0.01. That's pretty small. It's pretty tight. So we want to be really sure in our findings here. We're supposed to test the claim that 27% of the peas will be yellow. Well, they didn't say less than 20% or more than 27%, so it would be this one. Different from 27%. Okay. What is the test statistic? Well, let me open StatCrunch. Now this is proportion stats because we have a p-hat, right? P-hat is 133 over 433. So I'll go to proportion stats, one sample with summary. The number of successes was, there was 133 yellow peas, and I misspoke. 433 is not the total, right? That's just the number of green peas. So it needs to, the number of observations then is 433 plus 133. So that's 566. All right. And we are doing a hypothesis test for 27%. So I put my 0.27. I'm ready to go. Click compute. Gives me everything I need. The z-stat, the test statistic, and the p-value. Z-stat is the test statistic. So minus 1.88 is mine. With a corresponding p-value of 0.0606. All right. Now that's a 6% chance of being wrong if I reject. 6% is small, but it's not small enough. So 6% is too much risk for us today. Then we will fail to reject on that enormous p-value being bigger than our limitation, alpha.
I feel like if on our homework they always said it like that, I would have gotten it every time. That's the only time I've ever seen them answer it like that.
There was one on the homework that
Okay.
was like that, but just one.
Or the quizzes, I guess is what I should.
My p-value is greater than my alpha.
Yeah, mine was up here too.
Oh, yeah. I have a different alpha, but
Okay, so then, what now?
There's insufficient evidence. First one.
The first one. It basically says you don't have enough evidence to reject. Yeah. Child booster seats with the head injury condition unit number. Open and stat crunch. This won't be, it'll be T-stats, yeah. So, stat, T-stats, one sample with data. And we're doing a hypothesis test for to see if it comes from a sample with a population less than 1,000. So mu is equal to 1,000 or mu is less than 1,000. Don't forget to change your inequality right there. Because if you forget to change it, then you'll get the right test statistic, but it'll be the wrong p-value. And I get this test statistic that is way far in the tail with a correspondingly miniature p-value. To 3 decimal places is minus 4.152. And the p-value to 4 decimal places is 0.0044. State the conclusion. Well, it was at the 0.05 significance level, so I should always reject unless the p-value is bigger than this, in which case the likelihood of being wrong for rejecting is too great. And my p-value is 0.0044. So there's hardly any risk associated with rejecting. I'll be right, more than likely. So I shall reject H0. I do have evidence to support the alternate hypothesis. What do the results suggest about the child booster seats of meeting the specified requirement? There is not strong evidence that the mean, wait a second. There is strong evidence that the mean is less than 1,000, even though one of them was greater than 1,000. So it's like these booster seats suck, but one of them was okay. All right, difference of two means. Treatment group and placebo group. Okay. Why does that keep happening? T-stats, 2 sample with summary. And so my treatment group had a mean of 2.37 with a sample standard deviation of 0.95, and that was with 25 patients getting treated. In the placebo group, we had a mean of 2.67, standard deviation 0.68 on 33 patients. And if you're testing the difference of two means, mu1 minus mu2 is always 0. However, what are they asking us to check? Test the claim that they're from populations with the same mean. So that means we're using a not equals. They don't even tell us what X bar is. I don't even know what they're measuring here. So, but they could have said, check to see if the mean of the treatment group was less than the placebo group or whatever. Then I should make sure that I use the not equal symbol right there. Now I can compute, and I've got my numbers. So my t-stat is minus 1.34. My p-value to 3 decimal places is 0.188. And now to state the conclusion. Well, 18% chance of being wrong is big, right? I don't want an 18% chance of something bad happening to me, no matter what it is, really. That's too much. So I'm not going to reject. I'm going to fail to reject. And if you fail to reject, you don't have sufficient evidence. This essentially says, I'll fail to reject. There is not sufficient evidence to reject. It's the most straightforward way you could do it. Now we want a corresponding confidence interval. If you go right back to the output window you have, you can go to Options Edit, and it opens up with all the same numbers typed in, and then you can change it to the confidence interval. Okay, now we are doing I have a 10%, my alpha is 10% here, and it's a two-tailed test, right? So then it's this picture. My alpha is 10%. It's a two-tailed test. So I had 0.05 over here and 0.05 over here. There's 0.90 in the middle, so I should be 90% confident. So then now I have my confidence interval. 3 decimal places, minus 0.677. Up to 0.7, or excuse me, 0.077. And if you were out in the real world and this was a real thing, 0 is in this confidence interval. So it could very well be the case that the placebo group and the treatment group are giving you the same results, in which case your medication isn't doing squat. Bears. All right. Chest size and weight. So I'll open this data in StatCrunch and go straight to the stat regression simple linear. X variable is the first one, Y variable is the second one. There's nothing else to click except compute. You get a 2-page summary. The picture's on the second page. Yes?
What did you go to? You went to
Stat regression simple linear. Pretty good correlation, like you would expect. And they want me to produce the regression equation. Okay, well, here it is. Now it's got, it wants rounded to 1 decimal place, so minus 170.3.
And all we did was just do the X and Y variable, right?
Yeah.
Okay.
And then my slope is 9.8. What is the best predicted weight of a bear with a chest size of 44 inches? I don't know. Let me consult the p-value. So that p-value is 0.0105, which is less than my alpha, so I'm good to go for using the regression equation. So now I will use it. If it had been bigger than my alpha, then I would not use it. I would use the average of the y values. So with a chest size of 44 inches, I predict a weight of 260.9. Is the result close to the actual weight of 223? Here we are again. I don't know. What do they mean by close? Well, I'll tell you, it's not exactly the same, okay? And it doesn't seem to be very close, but it doesn't seem to be not very close. So I'll go with close.
What was your?
We just did that.
Yeah.
The one
Mine's like a
that
50-pound
actual-
spread.
Yeah, well, that's not very close at all.
Okay, good.
I don't even know if that's close.
I put it's not very close because I don't have a not close.
Okay. And for all I know, I could be wrong here. I mean, so I have what, 36 pounds, 37 pound difference.
Well, and when I look at the chart, it seems to be they're kind
Yeah,
of
that's
at
a good
20
idea. How-
20 pounds.
Well,
In the equation? Or your
what do you think? Does that seem reasonable for the bear to weigh a negative amount?
That's why I'm like, I don't know where I went wrong with what I'm trying to say.
Probably copied their own equation out wrong.
chest size and a Y variable for weight.
Mm-hmm.
And that's it, we just hit compute after that, right? And then so I got -227.1 plus 11.89.
Times X.
Do that.
And then X is not just size.
So 50, okay.
All right, see what I did wrong. Of course, I bet you, look right here, it's gonna say I was wrong about the being close. It's probably gonna be not close. Yeah. Not very close. So 37 pounds is not very close, I guess. I mean, it's a bear. I wouldn't think that 37 pounds is that much, but. And then I missed something else too. There was another mode.
Oh,
I had three.
I had
Yes.
three modes too.
Did you get the 13th connection?
I went back to 16 because my alpha, I had to fail to reject on 16 because my p-value was greater than, we'll say it's significant something. So I failed to reject, there's insufficient evidence to explain.
So while it's certainly true that
Are you serious?
that's the reason you fail to reject, but try and keep in mind that you failing to reject because if you had rejected, there's a hefty chance you'd be wrong.
So there's,
So we were just-
Same.
And we don't want to be wrong. We're doing research here, right? So in an effort to be correct, we'll fail to reject.
That's the best thing is,
Because if we always only have that rule about who it's greater than alpha, it's less than alpha, then we kind of lose sight of what that number means. It's a probability. And it's telling us that if we always reject, it's the probability we'd be wrong if we did. And then so you can even know to what extent it was smart to reject or fail to reject. If the p-value is like almost 0, then it's like, heck yeah, we're rejecting. But like earlier, I had a p-value that was 50-something%. It would be like a major mistake to reject there.
okay. So are you saying that the p-value is closer to the significance level, then it's insufficient or sufficient?
It is only sufficient evidence if you have rejected.
Gotcha.
Rejecting is the act that hypothesis testing is all about. The p-value tells us the probability that we'd be wrong if we reject. And the evidence is supporting our ability to reject.
It's 2 R's there.
So if we rejected, we have evidence.
But if we fail to reject,
We don't have evidence. If we fail to reject, we don't have evidence to reject. If we reject, we do have evidence to reject. And sometimes instead of saying warrant rejection, we'll say support the alternate. So your conclusion would be fail to reject H0, there's insufficient evidence to support the claim.
Right, right.
And then you'd have, there is not strong evidence that the mean is less than 1,000, but one of the booster seats is greater.
It's greater than